Alright, so of course user error here. What I did is I picked the wrong, got the wrong bit going. And that's very easy to do. So what I was doing is I was measuring the complement of the bit. There's an active low and an active high signal, and I got them mixed up, of course. So what we want is the active high going into this gate here. And so I want to test the active high signal being generated. And I was measuring the active low one. We want to know where's the active high of this group 1 instruction signal. And I didn't notice, so I was looking at the active low one. So we'll get the active high one going here, which is right next door. So again, we still have the -2 volts going here. And the active, from the active high, which is right here, J103. And yep, -2 volts coming out of that guy. Now, that looks like it's just a simple inverter. It just has 2 diodes on it. So we've got the -2.0 volts coming out of that thing. Let's see what we have going into it. And yeah, the diodes look like they're okay. Let's see if I can manage to clip on there. And we have a good strong one going into that. Okay. Now, this is a group 1 instruction. And we have the active high is a -2 volts. So that's wrong. Okay. And we have a little inverter. And we have +4 volts going into that, 4.1. So we have this little inverter here, group 1. Group 1 is showing -2 volts. Okay, and we have going into that inverter, we have 4.1 volts. Okay, so the inverter is working. It's just, okay, we shouldn't have a 1 here. You know, we shouldn't have a high voltage. We should have a 0 here, because this is a group 1 instruction. This is active high, right? Active high. And this is group 1, active low. But it's showing 4.1 volts. So now, again, rinse and repeat. Why is this signal being decoded? Why is this signal 4.1 volts? How is this signal derived? So now we look in our little file. And actually we did that on the last step, because that's where I made the mistake before. We know it's coming out of this J104 gate. And we can confirm that. Yeah, 4.1 volts. Yep. So now, what is this? How does this J104 gate, how is that put together? Again, we look in the report file for J104, that gate. We looked it up before. That's the active low group 1 signal. Okay. And that has 2 inputs. It's a little NAND gate. I can tell by looking at the report file, but if you really wanted to look, you could look back in that modules file. Well, let's do that. It only takes a second. Look in the original source file to see how that signal is derived. Group GRP A1Q, I think I call it. Yep. With the underscore. The ones with the underscores are the active low. So that's, yeah, it shows a little NAND gate in here. Operate 1 instruction, and the MA register bit 8. So if it's an operate 1 instruction, or I should say if it's an operate instruction, right? Operate in the first cycle of an operate instruction. There's only one cycle to them, but if it's an operate instruction, that's one of the terms for that AND gate. And the other term is active low on the memory address bit 8. Active low goes in there. And that makes sense because the opcodes for a... I drew this out of the camera. So here's the NAND gate we're going to check out next. Okay. It should be an operate instruction, which is the 111 for that 7, right? That is a PDP-8 operate instruction. And then this next bit here has to be a 0. Okay, so that's what this NAND gate is supposed to be decoding for us. So we'll see what are the inputs to this NAND gate. So we have to find this NAND gate on the board and then measure its inputs. Okay, and again, I figured out this NAND gate by looking in the source file. The seq.mod source file told me that the equation for this group 1 signal is operate and not MA8. Or actually, it's a NAND. It's a NAND gate. And you can find that in that seq.mod file. So we'll go back now to our report file that will tell us where that NAND gate is, because I have no idea. GRPA1. So we just look for that signal, GRPA1Q. I've probably been there already, right? Yeah, that's that J104 thing. That got 2 inputs to it? Yep. Okay, so that's the J104 I was at earlier, when I shouldn't have been. Okay, so J104, I looked in the report file for this underscore group A1Q, which underscore again is active low. So we're trying to figure out why is that active low high when it should be low, because we have a group 1 instruction loaded, so that low signal should be low. And we'll double check that it's still high. Of course I can't read it. Is the voltmeter timed out? And it's just a matter of measuring these voltages through here. Yep, it's still got the 1 on it, still got the 4.1 volts on it. So now which of these diodes, let's measure the voltage going into the gate, and we'll see if we have what we should have. There's a diode 249, if I can get this probe on there. That's got a 5 volts on it. So I'll write that down here on my little AND gate, or NAND gate, 5 volts for that. And I'll measure the voltage on the other one. And then we'll figure out what's going on. I got minus 5 volts for that, so that's a good strong 0. I got a good strong 1 and a good strong 0. Okay, so now we're going to determine, okay, so this is what I measured here. Here's my NAND gate. I have minus 5 volts here, which is, a logic 0. And I have plus 5 volts here for this active low. And MA holds the instruction when you're doing an operate instruction. The memory address register holds the whole opcode. And that bit is a 0 for our clear accumulator instruction. I think it's clear accumulator and clear link. That's what why that's a 3, not a 2. And this bit here is a 0. So we have plus 5 volts for a active low 0 bit, which is correct. So this one is correct. So we can say 1 equals 1, and that's good. Now it is an operate instruction, and this is an active high signal. There's no underscore at the beginning of it. 0, that's wrong. It should be a 1, right? Because we have an operate instruction. If we had an operate instruction here with a 1, and this is a 1, nice strong 1 with that 5 volts going in there, we would get a 0 out here and everything would work. So we know that this operate instruction showing a -5 is wrong. R-O-N-G, wrong. So now, again, rinse and repeat. How is this operate instruction being decoded? Okay, this signal here is not correct. So we just have to keep going back to the next signal, next gate, to see what is incorrect. So I'll get another sheet of paper going here. I have no idea. It's the first time I turned this board on, so we'll see what happens. So again, I'm going to go back to the source file that will tell me how that signal is derived. So I'll search for this operate OPR. I just called it operate, and there's going to be a gate in here that is going to hopefully tell me. Okay, there's a little NOR gate here. This is a NOR gate. I can see that in the source file here. It says OPR1Q as it comes from a NOR gate. So I'll draw a little NOR gate here on the paper and show it to you here in a second. OPR1Q. OPR1Q. Okay, and there's 2 inputs to this NOR gate. 2 input NOR gate, exec 1Q, or underscore exec 1Q, and underscore IR underscore OPR. Okay, so here's the NOR gate that we're going to check out next. And one of the inputs to it is this exec 1Q. Now the things exec 1Q says we are in this state, exec 1. Okay, and that's the first and only of the execute cycles for a group 1 instruction. And down here, an exec 1 is the first cycle of execute for any of the instructions. Okay, whether it's a TAD or an ISZ or IO instruction or whatever, this exec 1Q will be asserted. Now it's an underscore, so it should be a low voltage. We expect to see a low voltage for this. Now this other signal here, IR OPR, this says, okay, it's decoding out of the instruction register that it's an operate instruction. Okay. So this signal also should be low because we have an underscore in front of it, and we're doing a group 1 instruction. So this should show that we have a operate instruction, low, low, giving us high, right? And what do we measure here? From our last sheet, we measured low voltage at the output here. We measured -5, which is wrong, right? So we're going to double check that when we find where this operate gate, this NOR gate's on here somewhere. So we're going to find out where that gate is, and we're going to measure these 2 voltages and see where this goes wrong. All right. So to do that, we go back to the report file and search for that signal name, OPR1Q. And, well, let's see, what is it going to tell us here? It is line 925. And it is telling us that a J92, 14.9 inches over, 2.6 inches down. So it's going to be, again, up in this corner somewheres. Somewheres up in this corner. we have J92. J92. And let's verify that it's got a low voltage on the output. Yep, I can see minus 5.1. Okay, so yep, we have the minus 5.1. I wrote down 5, that's good enough. So minus 5 volts, which is a 0, right? Anything like 0.6 volts or less is a 0. And some of these can be, minus 10 or whatever. That's fine. So we got the output we expect, the incorrect output, but that's what we wrote down from before, so we know that's bad. So I just wrote down, here's our little NOR gate. I just wrote down, 0 volts, 0, minus 5 volts is a logic 0, and we're saying that's bad because we're doing we're in the execute cycle for an operate instruction, and that should be a 1 because that's what the thing is supposed to be doing right now. Okay, so now we want to measure these two inputs and see which of these, maybe both of them are wrong. So we're going to measure the voltages for these two by going up here and measuring these diode voltages. Oh yeah, sometimes I write in here this is J92, so I don't forget. Sometimes you get confused. J92, which was I think right there. And now we'll measure these two OR terms and see what voltage we got for those. J92, we'll measure the first one, and we got 3.7 plus 3.7, so that's a good strong 1. And we'll measure the other one. What do we got there? We have minus 8.6. So that's a good strong 0. Okay, so now we figured out earlier that these signals should both be zeros, okay? And we have a 1 up here, okay? Because this is a nice strong 1. It's, well over 2 volts. So it's a nice strong 3.7, which is a nice strong 1. So that is bad. So mark that one bad. All right, this one down here is saying that we're executing an operate instruction, or the instruction register holds an operate instruction, and it's an active low signal because it's got the underscore on the front, and it's minus 8.6 volts, and that's a good strong 0. So we're in good shape with that. So now we have to figure out where does this exact 1Q signal come from. And that is one of the that's one of the state flip-flops. Okay, so that is outputting, looks like that signal is incorrect. So we have to trace that signal back to see where that comes from. Now, these state bits, the exact 1, 2, 3, and fetch and defer, those all go to backplane signals out these connectors here, out these things. So I'm going to look back on our test program to see if it is reporting an error with being an exec 1 state. And I can see here, probably not all that easy to see on the video, it's saying that the exec 1 state is low, should be high. So exec 1 state feeds into this and it is incorrect. So that flip-flop looks like it did not set. The exec 1 flip-flop did not get set when it should have. And that's probably the whole problem here. So now we have to go look at this flip-flop, find where its inputs and outputs and all that great stuff are, and trace through it and see if it is if it's really in this state that this is saying. And so far it looks like, yeah, it probably is messed up. So we'll go measure it and see what we got here. So we'll take this off here. I'll try to get it out of here. Ugh. All right. Let me go back to our little report file and see where this flip-flop is. So we just search it for the string exec 1 and see what it reports here. So it should tell us where, like, signals used all over the place. But all right, so the flip-flop is on line 63. So here's our little exec 1 flip-flop. And it is located, the output of this flip-flop is located 6.9 inches over and 11.6 inches down. So it's going to be down in here somewhere. So I'm going to draw me a little D flip-flop on this piece of paper here. Q bar, and D and T inputs. Like that. I'll draw me a little flip-flop and label out where all these various pins are. So there's the flip-flop that should be set when we go into exec 1 state. Okay, so we're going to try and figure out why that flip-flop has the wrong value. It should have a 1 in it. It looks like it's 0. Now some of these flip-flops are active low, so the only way to tell that is to again go back to the source file, the seq.mod file, and look at that flip-flop. And if you look at the source file, yeah, it's got active low input, active low output. So this is active low. And the output, the Q output is going to be active low. And the Q bar output is going to be the active high signal. Okay, so I'm going to note that here on my exec 1 because this in the source code has underscore exec. Okay, the D input for this flip-flop is fed by an active low signal underscore exec 1D. So I know the Q output is going to be active low. The Q bar output is going to be active high. Okay, so now I want to measure to make sure that, okay, active low, active high on these outputs of this flip-flop. So I'll go back to the report file. I think it was line 63. Yep. And I want to find out where my Q output and where my Q bar output are. So according to the report file, Q output is J50 and it is at 6.9 comma 11.6, and the active high output is J49 at 5.9 11.6. Okay, so now I know where the pins are for the outputs of this flip-flop, J50, J49, and now I'm going to measure these voltages. Okay, J49 and J50. Reset the voltmeter here. It likes to time out a lot. 7 inches over, 11.6 down. So let's see what we got here. 7 inches, well, let's see, 1, 2, 3, 4, 5, 6, 7. That's going to be around in here somewheres. J50 and J49 we're looking for. J50 and J49. Okay, so here are the two gates that are outputting for that flip-flop. And so we're going to measure J50 without blowing anything up. And it has 3.8 volts. Oh, there goes the ice cream truck. All right, and then J49. Oh, where's that? That's right there. And that's got minus 0.6. Back to minus 0.6. All right. So now we know that it should be an exec 1 state, and we have the active high is showing a negative voltage. So we know that is incorrect. We know the active low is a positive voltage, a good strong positive voltage, and indicating a logic 1, and that is incorrect. So at least the Q and the Q bar are showing opposite values. It's just not getting loaded correctly. So now, given that this is a flip-flop, we'll have to set up a little test to toggle this flip-flop and get this flip-flop to see, oh, is it loading a 1 when it should be? Is it loading a 0 when it should be? And that's a little more involved than going through here with a voltmeter. So we'll have to set up a little test program. We'll do another next part to get that going. So anyway, but you can see how to trace through these, and most of it can be done with a little voltmeter. Now it'll be a matter of setting up a little test loop, and there's a little program you can type in, a little test program with, to crank it through this exec 1 state and just repeatedly toggle that flip-flop and see if that flip-flop can clock signals into it. And something's not happening there, and you have to set up the oscilloscope and measure to see, oh, is it toggling in there and all that stuff. So I'll have to get that set up and make a second part on this video. Or actually, I guess it would be a third part. But anyway, there is getting us going and tracing back one of the faulty signals. And that's how you do it. So we're going to stop this for now and come back when we get the scope set up.